The entire global tech sector is currently locked in a zero-sum war to secure artificial intelligence compute infrastructure. Every major technology company requires immense volumes of specialized silicon to train their models, and they are all competing for space in the exact same manufacturing facilities. Tesla's internal compute demand is scaling at an extreme velocity. To power the transition to their Optimus humanoid robots, the upcoming Cybercab fleet, and the expansive Dojo and Grok training infrastructures at xAI, the company requires an uninterrupted supply of custom chips. Internal forecasting models revealed a strict physical limitation, known as the chip wall. This is a projected macroeconomic reality where the combined maximum output of the world's leading semiconductor foundries, primarily TSMC and Samsung, will be mathematically insufficient to meet Tesla's scaling requirements. Relying on those foundries also introduces severe geographic and geopolitical liabilities. Building the intelligence architecture for a massive fleet of autonomous vehicles and robots on a highly concentrated, fragile supply chain located entirely across the Pacific Ocean presents an unacceptable corporate risk. To survive the AI race and secure its physical robotics rollout, Tesla concluded it must transition from a fabless automotive client into a sovereign integrated device manufacturer. By domesticating the hardest manufacturing process in human history, Tesla aims to design, fabricate, and package its own silicon entirely in-house. Tesla initially attempted to bypass the impending chip wall through a traditional partnership. They signed a $16.5 billion supply contract with Samsung Electronics to manufacture the critical upcoming AI6 processor. Early in 2026, that strategy failed. Samsung's highly anticipated 2-nanometer prototype run suffered a catastrophic schedule slip, delaying production by roughly 6 months. This acute delay rippled through Tesla's corporate roadmap, pushing the critical AI6 mass production deep into late 2027 or 2028. It exposed the existential threat of outsourcing hardware development for embodied AI. Rather than accept the delay, Elon Musk made a ruthless pivot. He effectively fired his exclusive external partners and posted a 7-word announcement, declaring the launch of a domestic TeraFab initiative in exactly 7 days. Tesla is targeting an initial capacity of 100,000 WSPM, with a long-term goal of 1 million. WSPM stands for wafer starts per month, the standard metric for a factory's total output. Reaching 1 million WSPM would mean replicating roughly 70% of TSMC's total global output inside a single domestic footprint. Building an industrial empire of that magnitude within a single Texas footprint represents an aggressive, high-risk declaration of total silicon independence. The global build-out of AI infrastructure is severely constrained by raw electrical grid capacity. An NVIDIA H100 processor famously draws up to 700 watts of power. Tesla designed its custom AI architectures to achieve equivalent computational performance at a hyper-optimized 150 watts. Achieving that extreme 150-watt efficiency strictly dictates manufacturing at the bleeding-edge 2-nanometer process node. Traditional architectures fail at the 2-nanometer scale due to quantum tunneling. Electrical current leaks through solid matter, generating heat. The 2-nanometer process solves this with a DEAT all-around architecture. Wrapping the gate completely around the silicon channel locks electrons in place, preventing thermal leakage. Moving from nanometer physics to factory economics requires understanding yield curves. A yield curve measures the percentage of functional, usable chips produced on a single silicon wafer versus those scrapped due to microscopic defects. Early production runs at advanced nodes like GAA are notoriously volatile. Initial attempts frequently produce catastrophic yield rates, sometimes resulting as few as 30% usable dies per wafer. The true cost of the TeraFab is not the $25 billion construction budget, it is the tens of billions of dollars in operational cash burn required to agonizingly tune that 2-nanometer yield curve from 30% up to a profitable 90%. For decades, the bedrock of semiconductor yield management has been the ISO Class 1 cleanroom. These massive, energy-intensive environments utilize heavy HVAC infrastructure to filter out almost every microscopic particle from the ambient factory air. Musk polarized the industry by proposing to discard these traditional cleanrooms entirely. He publicly wagered that he could eat a cheeseburger and smoke a cigar directly on the 2-nanometer factory floor without ruining the silicon. His technical argument relies on wafer isolation theory.
He proposes keeping the product inside FALPs. FALPs, or front-opening unified pods, are sealed boxes filled with pure nitrogen gas, conceptually identical to how agricultural commodities are protected in controlled oxygen-free atmospheres during global shipping. Process engineers immediately identified the fatal engineering conflation in this theory. Successfully isolating the silicon wafer does absolutely nothing to protect the incredibly sensitive manufacturing equipment from the macro environment. Printing at 2 nanometers relies exclusively on EUV, or extreme ultraviolet lithography. This technology generates a 13.5 nanometer wavelength of light by bombarding microscopic tin droplets with high-power lasers tens of thousands of times per second inside a vacuum. To direct that specific wavelength of light onto the silicon, EUV technology utilizes ultra-sensitive optical mirrors. Cheeseburger grease and cigar smoke generate massive amounts of volatile organic compounds. Even if the wafer is safe inside its nitrogen box, the ambient factory air will inevitably interact with the lithography optics during routine machine maintenance or reticle loading. Contaminating a $200 million optical mirror with these compounds permanently destroys the tool's precision. If the mirror cannot focus the light perfectly, the factory's production yield drops to absolute zero instantly. Treating an atomic-scale manufacturing facility like an agricultural logistics problem invites catastrophic, fab-wide equipment failure. The current global semiconductor supply chain is deeply fragmented. Distinct companies handle logic printing in Taiwan, memory fabrication in South Korea, and final packaging in scattered facilities across Asia. Shipping sensitive components across the ocean creates massive data latency and bottlenecks at OSAT facilities. OSAT providers package these disparate chips together. The TeraFab blueprint disrupts this standard by combining logic, memory, and packaging entirely under one domestic roof. The new AI6 architecture strictly demands this unified packaging approach. By moving silicon directly from logic printing to memory integration in a continuous domestic pipeline, the physical distance data has to travel is minimized. This architectural requirement is directly tied to the end use case. An Optimus robot operating in the physical world must process high-definition, real-time video instantly, without any lag, to function safely. The TeraFab initiative physically re-architects the supply chain to unlock the zero-latency processing speeds required for physical robotics. This chart illustrates a stark divergence in Tesla's financials. While their legacy automotive revenue experienced a 10% year-over-year decline in 2025, the company allocated a record $20 billion capital expenditure specifically for the TeraFab project in 2026. This financial pivot is a definitive burn-the-ship strategy. To execute it, Tesla took extreme internal measures, physically halting legacy Model S and X production lines in Fremont just to clear factory floor space for Optimus assembly. But even with infinite capital and massive floor space, there is a final, inescapable physical bottleneck: the Dutch firm ASML. ASML holds an absolute global monopoly on extreme ultraviolet lithography machines. They are the only company on Earth that manufactures the tools capable of printing at the 2 nanometer node. ASML can only produce roughly 60 of these incredibly complex tools annually, and their entire production capacity is backlogged and spoken for through 2028. The companies monopolizing that order book, TSMC, Intel, and Samsung, are the exact competitors Tesla is attempting to bypass. A facility targeting 1 million wafer starts per month requires hundreds of EUV machines. Without securing priority allocation of those back-ordered tools, the TeraFab is physically incapable of scaling, regardless of how large the building in Texas is. If the execution is precise, Musk creates a new model for vertical integration, transforming Tesla into a sovereign AI infrastructure state immune to supply shocks. If the yield physics, contamination risks, or equipment bottlenecks are miscalculated, the TeraFab becomes a $25 billion monument to capital destruction.